Hey guys, welcome to the Pre-Calc Unit 7 review on sequences and series. All right, question number 1, it wants you to find the nth term rule 4, and it gives you two different sequences. First thing we need to do is identify what type of sequence is it, arithmetic or geometric, because obviously there's a different formula. So you just want to look at the pattern here. What are we doing to each number to get the next one? And I think it's pretty obvious here we're adding 3 each time. So it's arithmetic. All right, you don't have to write this formula down. I'm just reminding you guys for arithmetic, the a sub n formula is a sub 1 plus d times n minus 1. Basically, what we need to do is we need to identify a sub 1, which is obviously negative 4, and d, which is 3. So our a sub n rule is going to be a sub n equals a sub 1, so you put in the number, negative 4, plus d, which is 3, times n minus 1. You could clean that up if you wanted to, but you don't need to. In this application, you just want to write that down. Okay, the next one. What are we doing here? Going from the first term to the second, second to third, third to fourth. So in this case, I'm obviously multiplying 4 to 20 to 100 to 500, but notice there's also negatives in there. 4 to negative 20, so I'm multiplying by negative 5 each time. So this is geometric. All right, and the a sub n rule for a geometric series is a sub n equals a sub 1 times r to the n minus 1 power. So let's identify a sub 1 here. That's 4. What is your r? That's negative 5. Your a sub n rule then, or sometimes called explicit rule, is 4 times negative 5 to the n minus 1. All right, question 2 should be pretty straightforward. You don't have to show a lot of work here. It wants you to write the first 5 terms of the sequence. I will, because it's a review, show you all the steps to this. But again, you could probably just write out the numbers. Most of this is mental math. So in 2a, they give us an a sub n rule. A sub n equals 6 times n minus 1. Now, basically what I'm going to do for a sub 1 is I plug a 1 in for the n. I'm going to take the time to write out the first couple, and then if I can easily establish a pattern, maybe I'll just jot the last couple down. So a sub 1 is going to equal 6 times 1 minus 1. 6 minus 1, that's 5. A sub 2 equals 6 times 2 minus 1. 12 minus 1, that's 11. A sub 3 is 6 times 3 minus 1. That's 18 minus 1, that's 17. So I can see what's happening here. Each time I'm adding 6. I can probably do the last two in my head without writing all this out. So I have to take 17 plus 6. That's going to be 23. And then for a sub 5, 23 plus 6, that will be 29. So I've just listed out the first 5 terms. In this example, I'm not going to show a lot of work. It's pretty obvious here. All you're doing is subtracting 7 each time. So a sub 1 is already 90. A sub 2 is going to be 83. A sub 3 is going to be 83 minus 7, so what's that, 76. A sub 4 is 76 minus 7, 69. A sub 5 is 69 minus 7, that's 62. All right, so there are the first 5 terms of that one. Question number 3, write the recursive definition. So to write a recursive definition, you need 2 things. You must have a sub 1 and then a rule for the next term. So I always start by writing a sub 1 down. This is probably the most commonly missed question every year on this exam. That is part of your solution. I don't want to just see a rule for a sub k plus 1. I need to see a sub 1 and a rule for a sub k plus 1 or n plus 1, however you want to write it. It doesn't matter. I'll use that in this case. All right, well, let's establish what's happening to go from one term to the next each time. 2 goes to negative 6. Negative 6 goes to 18. 18 goes to negative 54. So clearly here I'm multiplying by negative 3. So I'm taking the previous term and multiplying it by negative 3. So I'll start by writing down negative 3. And then if I have a sub n plus 1, the previous term is just a sub n. Please make sure you put a box around both of these and not just this. If you just circle this but not a sub 1, you will lose a point. So this is the recursive definition, both of those. All right, B. I'm going to start by writing a sub 1 is 87. and then figuring out the pattern, 87 to 81 to 75 to 69. So 87 to 81, I subtract 6, then subtract 6. So each time I'm subtracting 6. Your rule for a sub, I'll use a k in this case. A sub k plus 1 is going to be a sub k minus 6. And that's your recursive definition. Question number 4 wants you to find the 1,000th term of this particular sequence. All right, 12, 17, 22, 27. So the first thing I like to do is establish the pattern. What are we doing each time? We're adding 5. So it's arithmetic. A sub 1 is 12. D is 5. So to find the 1,000th term, a sub 1,000, it's going to be a sub 1, 12, plus d, 5, times n minus 1, or in this case, 999. Obviously, this whole exam is going to be calculator active, and if I throw that into the calculator, I get 5,007. Now let's move on to sums. I want to find the partial sum of the following sequences. So when you see this, they mean by partial sum, it's not infinite, it's finite. So I want the sum of the first 20 terms. Well, I've got two different sum formulas, so I need to take a look at the series and see what's happening. 4 to 11, 11 to 18, 18 to 25. So here we're adding 7 each time. It's arithmetic. All right, so first of all, I've got a sum formula for an arithmetic series, and that's this, n over 2 times a sub 1 plus a sub n. So I can do part of this right now. Sum of the first 20 terms equals 20 divided by 2 times a sub 1, which is 4, plus a sub 20. I don't know what a sub 20 is. I got to find that. Okay, so I have an a sub n rule. I'm just going to kind of do this quickly. We've already established the a sub n rule from up above. It's going to be a sub 1, so that's 4, plus d, which is 7, times n minus 1, which is 19. All right, so let me throw that into the calculator real quick. I got 137. So 137 is the 20th number. That's the number you need to go right here in your sum formula. Now you're just going to multiply all that out on the calculator, and you should get 1,410. Okay, the next one, B, I want to find the sum of the first 6 terms here, and it says a sub n equals 3 times 2 to the n minus 1. Well, I've got a sum formula for geometric series. S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. So I need a sub 1 and I need r. Well, looking at this, I know r is going to be 2. So I know r is 2. A sub 1 is going to be what I get by plugging in a 1. So if I plug a 1 into the n, right here, I get 1 minus 1. That's a 0. 2 to the 0 is just 1. And 3 times 1 is 3. So a sub 1 is 3. Now I can use my sum formula. Sum of the first 6 terms is going to be a sub 1, 3, times 1 minus r, so 1 minus 2, all right, and that's going to be to the 6th power divided by 1 minus 2. And again, we're just going to throw that right into the calculator. Please use your alpha F1 to create a fraction here so you don't have to worry about order of operations and any of that, but you should get 189. Okay, last one on this page. Find the sum of the infinite geometric series. So again, we have a formula for the sum of an infinite geometric series. Because it's the review, I'm going to write it down over here. That is simply a sub 1 over 1 minus r. And what's kind of cool about it, all right, if you watch the video and watch me derive this, it's this formula right here without the 1 minus r to the n. Because what happens if r is less than 1, and remember this only works right here if the absolute value of r is less than 1, so such as 1/2. Because if you take 1/2 to the infinite power, that's 0. So this whole fraction here, or this whole expression just becomes 1, and that's a sub 1 times 1. So that's just a little aside. You don't really need to know that, but you do have to make sure r is less than 1. So let's check out our series here. 20 to 10, 10 to 5, 5 to 2.5. So obviously here I'm either dividing by 2 or multiplying by 1/2. So R is 1/2. Indeed, that is less than 1. Now what's cool about this, I know this is calculator active, but these usually work out very nicely. You can do these without a calculator. So if I want to find the sum of the infinite series, I need a sub 1, which is 20, over 1 minus 1/2. So check this out. We can actually do this very easily without a calculator. It's going to be 20 over 1/2. Copy, change, flip. 20 times 2, that's 40. So the sum of this infinite geometric series is exactly 40. In question number 7, we are given an arithmetic sequence. That's important. They have to tell you what type it is. Because we're given non-consecutive terms here. I need to find a sub 1, a sub n, and a sub 40. Notice those are not consecutive, so I can't just subtract those two to get d. I have to recall my formula for finding d. Again, because it's the review, I'll just write this out. A sub n minus a sub m over n minus m. So in this case, that ends up being 33 minus 12 over 6 minus 3. All right, that's 21 over 3. That is 7. So I know d is 7. How do I get a sub 1? Well, I just like to work backwards. You can plug into a formula, but I just find it a little quicker for me just to work backwards. If d is 7, all right, and we have to go backwards, we are subtracting it. So a sub 2 would be 5. A sub 1 would be 5 minus 7, or negative 2. So a sub 1 is negative 2. Your a sub n rule. Again, at this point, you should have it memorized. It's going to be a sub 1, so negative 2, plus d, which is 7, times n minus 1. And again, you could clean that up. You could distribute the 7 if you wanted to and combine like terms, but you certainly don't need to. And then a sub 40, which is simply plugging a 40 in for the n. You get negative 2 plus 7 times 39. And throw that in the calculator. I got 271. Okay, very similar question here, except now we're talking about a geometric sequence. A sub 1 is 4. A sub 2 is negative 20. This is actually even easier than I wanted to do. Just for the exam, make sure you know how you would do this if those were non-consecutive. Because being consecutive, it makes it a little bit easier. R is simply a sub 2 divided by a sub 1. So in this case, negative 20 divided by 4, negative 5. And a sub 1 they already gave you. So a sub n in this case is going to be a sub 1, 4, times r, negative 5, to the n minus 1. S sub 5, so the sum of the first 5 terms. All right, you don't want to write out the 5 terms and then add them together. You want to use the sum formula. So it's going to be a sub 1, which we said was 4, times 1 minus r. So here's where you have to be careful. 1 minus r. In parentheses, you need to put negative 5, and then you have to take that to the 5th power. This becomes very challenging when your r value is negative. All right, please be diligent with your use of parentheses because I have to take this to the 5th power, which is going to end up being a negative. Your calculator will do it all, but if you don't put parentheses in there, your calculator will do it incorrectly. And then we'll do that over 1 minus negative 5. Okay, so if you enter that correctly in the calculator, you should get 2,084. Okay, in the next group, summation notation, it says write an expanded notation and find the sum. And it appears more daunting than it actually is. First thing I want to do is expand. The way we expand is we find the first 3 terms and the last. And remember, this is summation notation. Don't put commas between the terms. You have to put plus signs. Okay? All right, so if I plug in a 1, I get 2 to the 1st power. That's just 2. So I think that's pretty straightforward. Plus, then I plug in a 2. Well, I get 2 squared, so that's going to be 4. Plus, then I plug in a 3, and I get 2 cubed, so that's 8. Plus, dot, 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 plus, and then you plug in this for the last one. That's going to be 15, 2 to the 15th. So obviously you want to use your calculator there. I got 32,768. So there it is in expanded notation. Now, how the heck are we going to find the sum? I don't want to find all 15 of those terms. So what we do next is we identify what type of series is this? What are we doing each time? So if you look here, I'm actually multiplying by 2. That means it's geometric. I use my geometric sum formula. R is 2. So my geometric sum formula for 15 terms, it's a sub 1, so 2, times 1 minus r, 1 minus 2, to the n, so that'd be the 15th, divided by 1 minus r. And if you throw that into the calculator, you get this large number, 65,534. All right, so the next one, same thing. It's a summation. What I want to do is start by plugging in a 1 here, evaluating that, get the first 3 terms, and then the last. So if I plug in a 1, 3 times 1 is 3, 3 minus 4 is negative 1. Plus, then I plug in a 2. 3 times 2 is 6, 6 minus 4 is 2. Then I plug in a 3. 3 times 3 is 9, 9 minus 4 is 5, that's good enough. Now I plug in the last one, wow, 700. So 3 times 700, all right, it's 2100 minus 4, that's going to be 2096. So again, I'm certainly not going to calculate all 700 of these numbers and then add them in my calculator, but I do want to come up with a formula. So take a look. What are we doing each time? -1 to 2, 2 to 5, well, I'm adding 3. Since I'm adding 3, this is arithmetic. I'm going to use my arithmetic formula to find the sum of the first 700 terms. Remember here, that tells you how many terms you have. So n over 2 is going to be 700 over 2 times the first term plus the last. And that's the great part about expanding this, is you already know those once you expand it. And that's why I make you do the first 3 and the last, because you need that last one in an arithmetic sum. Okay, and you throw that into the calculator. I got 733,250. Okay, this is a relatively simple application problem. We forgot to put day 5 in the calendar. I don't know if you guys got my Brave Square post, but there is a video for day 5 that wasn't originally assigned to you guys. So this question here is a little bit challenging. Please feel free to go back in and watch that video, because we do a couple application problems like this. So this says a bacteria colony doubles in size every day. If the amount of the colony on day 1 is 50, write in expanded notation the first 6 days. So it doubles, all right? What I need to do is I need to write a series that just doubles, and it starts at 50. Okay, well, that's not too hard. A sub 1 is 50. A sub 2, well, you double that, that'd be 100. A sub 3, you double that, that's 200. A sub 4, you double that, that's 400. And A sub 5, you double that, that's 800. 6 days. All right, one more. A sub 6 equals 1600. I need to read the directions. All right, so now it says find the explicit definition, the nth term. Well, it doesn't specifically ask me to identify this type of sequence, but clearly this is going to be geometric, right? 50 times 2, 100 times 2, 200 times 2, so on and so forth. It's geometric. I need to know A sub 1. Well, we already established that's 50. I need to know R. Well, double, so that's 2. So the explicit definition, the nth term rule, you might hear A to the n rule, is going to be A sub n equals A sub 1, which is 50, times R, which is 2, to the n minus 1. Now, here's where it gets a little confusing with these application problems. It says, how many bacteria are there after 9 days? Well, the population doubles every day. This is not a sum question, because after day 2, there is not 150 bacteria. After day 3, there's not 350 bacteria. So believe it or not, this is not a sum, this is an A sub n. So I want A sub 9. 50 times 2 to the 8th. And if you throw that into the calculator, you get 12,800. You just have to be aware of that. Sometimes, well, usually with an arithmetic, if you want the total, it's going to be a sum. Geometric, usually not, because the population or the value is increasing or decreasing at a certain rate. So if you want what that actually is at the end time, in this case 9 days, it's an A sub n rule. Question 11. An auditorium has 50 rows of seats. In the first row, there are 32 seats, and each successive row has 3 more seats than the row before it. Write the recursive definition of the sequence. So before we get to that, I always like to list out the first few terms just to see what this looks like. So A sub 1 is the first row, 32. A sub 2, each successive row has 3 more seats. Okay, so that'd be 35. A sub 3 equals 38, so on and so forth. So I can see what's happening here. I'm just adding 3. All right, it's arithmetic. A sub 1 is 32, and my value for D is 3. So write a recursive definition. Remember, the first thing you want to write down is A sub 1. You have to include that in the definition. So A sub 1 equals 32. Then you need a rule for A sub n plus 1, A sub k plus 1, whatever notation you'd like to use. I'll use n plus 1 here, which relies on the previous term. So what are we doing to the previous term? Well, we're adding 3 to it. So I have to represent the previous term. So if the next term is A sub n plus 1, the one that comes before that is simply A sub n. And what are we doing? We're adding 3. So this is the recursive definition, both parts. Is it arithmetic, geometric, or neither? Why? Obviously, it's arithmetic. We already established that. Because you add 3 to each term. Find the number of seats in the last row. So the last row is going to be A sub, how many rows does it have? 50. And it's arithmetic, so it's going to be A sub 1, which we established was 32, plus D, which we said was 3, times n minus 1, or 49. Okay, and we'll throw that into the calculator. I got 179. So the last question here, it says find the total number of seats. Total number is going to be your sum, right? If you think about it here, the total for the auditorium is not 179. That's how many are in the last row. So I'm going to use my sum formula for an arithmetic. I should put a 50 there, sorry. There's 50 seats, so S sub 50. Let me just erase that. 50 rows in that. So that'll be 50 divided by 2 times the first, which is 32, plus the last, which is 179. And that gives me 5,275. Okay, another application problem here. A friend of Mr. Ward's recently purchased a Harley-Davidson motorcycle. The purchase price, brand new, was $18,000, and this model is said to appreciate at a rate of 4% per year. What will the value of the bike be for each of the next 3 years? So we're appreciating. That means we need to multiply by something more than 1. So A sub 1 is pretty straightforward. That's the purchase price. A sub 2 is going to be that purchase price times 1.04. That's what we call the growth factor, right? If it increases 4%, you have to multiply by 1.04. And let's see what I got by doing that. That was 18,720. A sub 3 is going to be that value, 18,720, times 1.04. Okay, and that got me $19,468.80. So there it is for the next 3 years. Find the A sub n rule. Okay, so for the A sub n rule, I need A sub 1, which is clearly 18,000. I need R, which is 1.04. And my A sub n rule is going to be 18,000 times R, 1.04, to the n minus 1. Now it says, what will the bike be worth when Mr. Ward retires in the year 2035? That is sort of a joke. He's not going to be teaching that long. But because this is an application problem, we have to kind of read into the context. It says, a friend of Mr. Ward's recently purchased. Now, I know we just turned 2021, but we're going to assume we're talking presently, 2021, retires in the year 2035. So my value for n is going to be 2035 minus 2021, or 14. So to figure out what's going to be worth then, I need a sub 14. All right, this is 18,000 times 1.04 to the 13th power. And throw that into the calculator. I got $29,971.32. The last two questions. 13, a payment of $4,000 is made every year to a Roth IRA. The account earns 9.5% compounded annually. What is the account's balance after 25 years? So this is the annuity type of problem. You put money into an account every single year. It gains interest all along. What's it worth after so many years? All right, this is a future value formula. Again, it's not necessary that you write it out, but I'm going to because it's the review and for the sake of review. So we had an a sub n. It's just the geometric sum form, but we rearrange some of the terms. Equals a sub 1 times, in parentheses, 1 plus little r. So that's just like if it gains 5%, it's 1.05. If it gains 20%, it's 1.20. To the n minus 1 all over little r. So it's a pretty straightforward formula. And this is just going to be a plug and chug type problem. A sub 25 years. A sub 1 is how much you put in every year. So you have to make sure you understand that. I could say you put in 500 a month, in which case you have to multiply 500 times 12. Or if I say you put in 2,000 every 6 months, you have to take 2,000 times 2. Just make sure you understand this is the annual contribution. Times, my interest rate is 9.5%. It's going to be 1.095 to the n, so to the 25th, minus 1, all over 0.095. All right, and I got, let's see, throw it in the calculator, $364,983.74 rounded to the nearest cent. All right, and the last one. This is a doozy. It says use mathematical induction to prove the following. So we have 3 steps for an induction proof. Show it works for n equals 1. Assume it works for n equals k, and prove it works for n equals k plus 1. So the first step is to show it works for n equals 1. I have to write small here, so I don't know how much room I'm going to have. So there's a couple ways you can get that. N equals 1 is simply the first term, so 1 squared is 1. Or you can take your rule and plug a 1 in there. That's usually what I do, but it's not the only way. So 1 squared equals 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Well, that's 1 here. I get 1 times 2 times 3 over 6. That's 6 over 6. 1 equals 1. All right, so I took my time there. I showed that it works in the first case. Because I might run out of room, I don't think so. I'll do it right underneath here. Show assume. So assume it works for n equals k. And what we're saying here, I know it might seem kind of silly, but what we're saying is k can be any term in this series. It can be the 10th, it can be the millionth, it can be the billionth. So we're going to assume it works for any term. What that's going to give me is this stuff here, and I replace that with a k, and I replace all of these with a k. All right, so that's going to be 1 squared plus 2 squared plus dot 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 plus k squared equals k times k plus 1 times 2k plus 1 all over 6. And this is the critical step. Prove n equals k plus 1. This is what's critical. I need to use all of this here. Because to get to n equals k plus 1, you have to use n equals k. You have to use all of this here. So the first thing you do is you rewrite this exactly the way it is here to start the next one. 1 squared plus 2 squared plus ... plus k squared plus. Now I need my k plus 1. That's the next term. It's got to have all of these plus the next one. Well, how do you get that next one? You take our rule, which is squaring, and you put a k plus 1 in place of the k. So that'll be k plus 1 squared. Now on the other side, I replace all of these k's with k plus 1, and we put them in parentheses. So any operation that we're doing to k, you have to do that to the k plus 1. So it's going to start with a k plus 1. That's this. But I wrote it as k plus 1. Now I have k plus 1 plus 1. And then I have 2 parentheses, k plus 1 plus 1. All of that over 6. Now here's the critical step, right? And here's why we have to write this out. We need to understand that these two things are equivalent, exactly the same. This is also equivalent to that. So what I'm going to do is substitute that expression in for this part of the sequence. All right, and that's called the bridge, the beginning, the end. The reason it's called a bridge is we connect them and we replace that. All right, so I'm going to use a different color here, basically to show you guys. You substitute in here. That's going to give me k times k plus 1 times 2k plus 1 all over 6. And then we bring the other stuff down. Don't forget, we've got the rest of this that we have to bring down. So that will be plus k plus 1 squared equals, now I'll do a little bit of cleanup here, but I don't want to multiply anything else. I want to work on some algebra. So that's going to be k plus 2. This is going to be 2k plus 2 plus 1, or 2k plus 3. Now, right now, I don't want to simplify this. You could do that. I like to call it the brute force method. Just multiply all this stuff out. It's going to take a while, but I think we can use factoring to streamline this process. So the first thing I need to do is I need to combine these two terms. All right, well, I'm simply going to do that by getting a common denominator here, and it's going to be 6 over 6. So now let's combine my numerators. That's going to give me k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6. I'm not going to do anything over here yet because I don't know how much I need to do. I want to work with this to try and simplify this. And again, you could do brute force. You could multiply all this stuff out. You could FOIL that out, distribute the 6. But one of the things I notice, I've got two fractions. I've got the 6's in place already. I also notice that I have a k plus 1 here and a k plus 1 squared there. And then I see a k plus 1 here. So maybe I take these two and I factor them out as a single term. So I take out a k plus 1. And then what would you have left in the parentheses? Well, you'd have everything here except that, so k times 2k plus 1 plus, and then over here, since you have two of those, you just take one away, so that leaves you with 6 times k plus 1. So now look at our two expressions. I've got the 6's in place. Those are the same. Now I've got this k plus 1 factor here and a k plus 1 factor there, so I'm good. All I would need to do now at this point is to get this stuff here equal to that stuff, and then both fractions would be equivalent. So I think that's pretty easy to do. I'm just going to distribute here, distribute there, clean that up, and I should have a trinomial. Here, I'll just do FOIL and get a trinomial. So I'll actually do that next. That gives me k plus 1 times k times 2k is 2k squared. I've got a 3k and a 4k. Combine those, you get 7k, and 2 times 3 is 6. So this is as far as I'm going to take that expression. I just now need to get this to equal that trinomial. And like I said, it's pretty straightforward. 2 steps and I'm done. K plus 1 times 2k squared plus k plus 6k plus 6 all over 6. And then one more. I'm just going to combine those like terms right there. So that's k plus 1 times 2k squared plus 7k plus 6 all over 6. And that's exactly what we have over there. And we're done. Wow, we made it finally. Thanks for watching, guys. That concludes the Unit 7 review. Do not hesitate to reach out if you have any questions, and we'll see you in class soon.